This is the second part of the 11th lesson in heat transfer, focused on steady-state, multi-dimensional conduction heat transfer. In the second part of the lesson, we will talk about how to create a numerical mesh for use in the finite volume method of approximating solutions to multidimensional conduction heat transfer problems. By the end of this lesson, you should be able to explain what a numerical mesh is. You should be able to label the components of a mesh, including the nodes and the faces. And you should be able to identify interior volumes in the mesh and distinguish them from boundary volumes in the mesh. On with the lesson. There are 3 steps to a finite volume analysis. The first step is to discretize the domain. This means that we will create what is called a mesh that will represent the physical problem. The mesh is made up of small, interconnected volumes. The volumes are small, but not infinitesimal. Infinitesimal volumes are only applied in differential analyses. The finite volume method is not a differential analysis. It is a numerical analysis. Some volumes are adjacent to the boundary of the physical problem. However, most reside in the interior of the physical problem. The second step of a finite volume analysis is to derive the algebraic equation that governs the heat transfer in each volume. I have 2 pieces of good news. The first is that most and many volumes share the same governing equation. The second piece of good news is that we only have to do the derivation one time. Once we have completed the derivation, we can use the governing equation over and over again in many different problems. Learning how to derive the governing equation, however, is an important skill to develop in heat transfer. Finally, the last step of a finite volume analysis is to solve the coupled set of algebraic equations. We will look at linear algebra techniques because the method of finite volumes results in a coupled set of algebraic equations that are linear. Solving these equations will be the focus of the 12th lesson. In the second part of this lesson, we will look at the mesh generation, the first step, what is called discretizing the physical domain of the problem. This is a 2-dimensional problem. We will focus on 2-dimensional problems in this course, but the methods applied to 2-dimensional problems are easily extended to 3 dimensions. The interconnecting lines represent what is called the numerical mesh associated with the heat transfer. The volumes are given an extent in the x and y direction, delta x and delta y. Where the lines cross represent node points. The nodes are the first component of any numerical mesh. I have highlighted the nodes at this particular location in the mesh in green. There is a node associated with the volume of interest, and there are also what are called neighboring nodes. These nodes are the neighbor to the node of the volume of interest. We use the variable m and the variable n to count the nodes in each direction. Thus, the variable to the right is the m+1 node. The variable to the left, the m-1 node. The node above, the n+1 node. And the node below, the n-1 node. It will be convenient in future lessons to replace these node indices with cardinal directions, north, south, east, and west to keep equations a bit simpler and help us remember what these indices represent, positions of nodes in the mesh. Each node resides at the center of a volume in the mesh. The volume is highlighted in red. The volume has faces. There are 4 faces in this 2-dimensional mesh. If the mesh were 3-dimensional, the volume would have 6 faces. Heat transfer occurs across the faces of the volume in the mesh, just like heat transfer occurs across all control volumes in heat transfer. Let's look at some examples of meshes. Here are 2 examples of meshes for 2 different problem geometries. In the mesh on the left, the physical problem includes a sloped surface. Nodes are located on the boundary of this sloped surface. These volumes have a subset of the volume in the middle of the mesh. They are smaller than the volumes in the middle of the mesh. But definitions such as this are perfectly acceptable. The problem on the right features a bracketed shape. Here, nodes are placed at the corners and on the boundaries. There are no interior volumes in this particular mesh, as all of the nodes reside on the boundary of the physical problem. In the first mesh on the right, however, volume number 6 is an interior volume. Its faces are all interior, and the node resides on the interior, while the remaining nodes reside on the boundary of the problem. These are called boundary nodes, while volume 6, this node, is called an interior node. We will follow 4 strategies when creating a mesh. The first strategy is we will put nodes on the boundaries. We will store information about the boundary at the boundary nodes. The information we will store will be related to the boundary conditions that we have seen in heat transfer so far. Known temperature boundaries, known flux boundaries, and boundaries in which there is convection heat transfer, or some mixed multi-mode heat transfer that can be represented with a thermal circuit. Interior volumes will feature 1 node at their geometric center. Boundary volumes have 1 node coincident with the boundary, and the volume is smaller in size than an interior volume. We have seen this in the previous examples of the meshes. Volumes on the boundary nodes are smaller than volumes associated with interior nodes. Finally, we will use the index variable m to count nodes in the horizontal direction, and the index variable n to count nodes in the vertical direction. Let's practice creating a numerical mesh for our problem from the textbook. This problem is based on the 67th problem in Chapter 4 of your textbook. A common arrangement for heating a large surface area is to move warm air through rectangular ducts below the surface. The ducts are square and located midway between the top and bottom surfaces that are exposed to room air. You might imagine this wall as being the wall of a large building to be heated. Here we have a concrete wall with square air ducts in the wall. The surfaces of the wall are maintained at 30 degrees C by the room air. Warm air is passed through the ducts, maintaining the interior surfaces of the ducts at 80 degrees C. We are interested in knowing how much heat is transferred from the warm air in the ducts into the room. When creating a numerical mesh and identifying the numerical domain in which that mesh will reside, it is always good practice to look for lines of symmetry in the original problem. This particular problem features 3 lines of symmetry. Lines of symmetry are excellent boundaries because we know that the temperature gradient is 0 on these surfaces, and so they are adiabatic. There is no net heat transfer across lines of symmetry. The 3 lines of symmetry in this problem are located at the midplane in the wall, and are located at the midpoint between 2 rectangular ducts, and at the midpoint in a particular duct. If we are to analyze the heat transfer in the numerical domain denoted by the shaded purple rectangle, we would obtain the same distribution of temperature as this in this purple square. We'd have the same distribution of temperature below it, to the right of it, and to the bottom right of it in these other quadrants. There is no need to analyze the entire system because all of the information required is contained in this one unit. This unit is repeated over and over again in the remaining part of the wall. We are thus getting the maximum amount of information for the fewest number of nodes required. Here is a numerical mesh for approximating the heat transfer in the air-heated surface, in the numerical domain identified in the previous slide. The boundary conditions to apply to this numerical mesh are that we have the room air temperature maintained on the top surface. We have the warm air at 80 degrees C maintained at the interior surfaces, representing the square channel. The lines of symmetry are modeled as adiabatic surfaces with no heat transfer. Each orange dot represents a node in the mesh. Faces are indicated by dashed red lines. Here, an interior node and an interior volume is highlighted. And here, a boundary node on the top left corner, what we will call the northwest corner of the mesh, is highlighted. This volume is 1/4 of the size of the interior volume. This numerical mesh is relatively coarse. That means that it features only a few nodes. In particular, there are only 43 nodes. The approximation to the solution to the heat transfer in this 2-dimensional conduction heat transfer problem can be improved with a finer mesh that features more nodes. Here is an example of a finer mesh. As you can see, the number of nodes has increased, and the size of the volumes has decreased. In this finer mesh, there are over 10,000 nodes representing the problem, which will produce a much better approximation to the heat transfer inside of this air-heated wall. When possible, it is desirable to use as many nodes as possible. However, there is a limit to how much improvement in the approximation to the problem one can gain by adding nodes, and generally there is a trade-off between the number of nodes and the computation time required to solve the equations, and the level of approximation to the solution required. One typically looks to find the right size numerical mesh with the appropriate amount of nodes to achieve the desired level of approximation to the problem. This process of finding the right level of approximation is called mesh refinement, and is a topic for advanced study in a computational fluid dynamics or heat transfer course that one might take in graduate school. This is the end of the second part of Lesson 11.